So I'm going to talk a little bit about how to compile sparse tensor algebra, especially when you have to deal with dynamism. So let me start by saying there's a lot of sparse data out there. If you look at things like data analytics, there's a lot of sparse data. Recently, machine learning, we are creating a lot of sparse data. And also science and engineering, historically, lot of these measures and simulations, our data was very sparse. To give you a little bit of a concrete example, what sparsity means, let me look at Amazon product reviews data set. So in Amazon product review data set, every person who ever bought something from Amazon is in one axis. All the products Amazon sells is in another axis. And every possible word somebody might have used to write their review is another axis. So if you try to store this as a dense data set, basically even Amazon data center might not have enough space to store this thing. However, if you look at closely, what you'll realize is most data here are zeros. So if you don't store the zero and only store the non-zeros, the data set might even fit in your laptop. So there's a huge difference in storage if you start storing data in a sparse fashion. So this is storage. How about performance-wise? So here I'm showing you matrix vector multiplication. So if you do just simple matrix vector, doesn't matter what the sparsity, all the data is present, it's a dense matrix in there, you get the same execution time. However, if you represent the data using a sparse matrix, at the beginning it's going to be more expensive than the dense because the sparse representation is more complicated, the amount of what you have to run to do this matrix multiplication is more complicated, so it is slower. But as you increase the sparsity or reduce the density, at some point there's a cutoff point and things become faster. And if you have a lot more sparse, things can get asymptotically faster. So as you go to left and left, it's actually really great. On the other hand, if you look at matrix multiply, gem doing dense matrix, and the cutoff point is a little to the left in here. So again, if you have not that much sparsity, the gem wins. But if there's some sparse data, and if you have a lot of sparse data, SPMM wins. So if you look at this spectrum in here, things like sparse neural network fits very nicely in the kind of right now range where SPMM started to kind of dominate. So people are trying to figure out whether you go dense or sparse, we have that boundary in here. However, if you look at what's out there, there's a huge amount of data that's a lot more sparse than anything in that range. So these things like fluid dynamics to social media networks, graphs, those things, you have to represent them as sparse data and compute them as sparse. Otherwise, your orders of magnitude slower. You are multiple asymptotes slower. So these data, it really, really matter to do this sparse operation. So let's dig a little bit deeper how this can be done, especially data representation. So I have this matrix in here. This is a matrix where the gray areas with letters are real data, everything else is zero. So if you do dense representation, I'll just copy it down and in a nice array, this is what memory represents data. This is great. Now, if you want to figure out where the value 1, 2 is very easy. I have a formula that will say what's the offset to that. In order 1, I can directly go and get that value. No problem. But the problem here is I am storing all the zeros. I have huge amount of storage wasted for zeros. So now how about if I eliminate the zeros? I only put the values that are actually present in here. I have a small problem here. Now what the hell is that value in location 3? I don't know. So if you only keep that, I have no idea what it is. So I need to add some metadata. So here I will keep each value will have a corresponding row and column coordinates as metadata. This is called the coordinate format used in industrial art. And now, given location 3, I can look up row and column and say, aha, this is row and column 2. That's what I find this value here. So one thing you will notice is this is very easy to do this way, but the other way is a little bit difficult, because if you are given row 1, column 2, to figure out where it is, you have to iterate over this entire array to find that location. So there's no order 1 locate in if you have this compressed representation. So what you find in a lot of compressed representations is certain accesses are cheap. For example, if I iterate to the entire array one after another, it's very cheap because I will go next is a order 1 operation. But if I have to locate some value, it's more expensive. So you have to be careful what you do and how you iterate or how you use these data structures. So another interesting thing in here is in coordinate format, people realize all the values in the same row, if there are a lot of values in the same row, the row value get duplicated in the row array. And that's waste of storage. So then people came up with this representation called compressed sparse row. This is the most popular sparse representation today, where we keep a position array at the beginning for number of basically rows, and it says where each row starts, and the last value you say where everything ends. So you just can go to the beginning of each row from that. And then the column say what is the column ID for each of these values that represented below. So column position array is the size of one dimension, we'll say n if the n squared. Columns and values are number of non-zeros. So in there. So in dense you have n squared. Now we went to n and two NNC arrays. That's what we need to represent this data. So this is a little bit more complicated tree structure, and you can have a bunch of these metadata structures to represent this. And if you look at this, this will look like a jumble of in there. But if you look carefully, what you can do is you can group them into levels. So what you can see is the first number of slices is dense. That means we have 3 slices because 3 size dimension. So it only need to know the size of that dimension in here. Next, you have row coordinates represented here, and then you have column coordinates in here. Because the first one is dense, there's a dense representation. And the second row is a compressed representation. And the last column for each compressed value, there's only one value in there, it's called a singleton representation. So we have this level format representations that some very complicated multiple arrays representing this multidimensional tensor. So if you look at these level representations, and here our original matrix in here, if I use dense and compress 2-level representation, we get CSR. And if I use compressed and singleton representation, I get coordinate. So the idea here is using this level representation, I can build much of this interesting representation. In fact, with these two representations, not only these two, we can build many other interesting representations out there using arrays. If you add 3 more level formats, basically you can get to all the practical array-based representations people see today. So this is great. So in a previous OOPSLA, we presented this work and showed that we can deal with array-based representations, and arrays are beautiful. But we have one small problem. So let me tell you this problem. So assume you have a friends graph. So something like Facebook is maintaining that. There's a bunch of people who are friends with each other. If you are a friend, there's L in here. And each person is a node in this graph. So if you just abstractly represented that, you can represent this as adjacency matrix. And the interesting thing is, while there are billions of people in the world, I only have a few hundred friends. So it's a very sparse matrix. So it's very nice to use a sparse representation. But there's a small problem that I'm going to explain. You're going to make friends, unfortunately. So you come to this conference and you found somebody you made friends with. Now what that means is now you have to update that graph. Now this what was 0 before has to become 1. If this graph was dense, it's very easy. Because every element has a location, I just go change that location from 0 to 1. But if I'm using a compressed representation to do this graph, Now try to add 1 to that thing here. The problem here is now what I have to do is I have to go move everybody, entire thing, because this data structure, and change the entire position matrix in here to do the representation. This is not that cheap. You have to do a lot of work in here. So in fact, let's look at doing something like a page rank computation. So what I'm showing here is doing page rank on a bunch of very large graphs that has probably 1.6 million to 255 million non-zeros in that. And this is also in a log scale, so there's a big difference in here. And so in our previous work, we showed that we can automatically generate this code. It's great. We have the data is represented using CSR, and we get really good performance doing this very large page rank. How about if I just want to add a single element to that graph? And it seems 255 million element graph to do a page rank computation takes less time than adding a single node to that graph, because I have to change the data structure drastically here. This is not good. So that means you can't make any more friends. Your friends is for life and nobody else become friends because I can't deal with it. So we had to come up with a different way. So in this representation, instead of doing using arrays, how about if you use a pointer-based data structure? So in here, what we are showing is one way of doing it, where the outer dimension is represented using a list in here, basically binary search tree. And for each nodes of that, you have the inner dimension, another binary search tree, bunch of binary search trees. So this is the representation of this matrix in here. Now, if I want to add this one element in here, what I have to do is some little bit of local surgery. I'll have to go move an edge in here, add this new edge, and change some pointers in a very small corner to add one element. It's much more easy to do that. So here's one representation in here. Of course, there are many other pointer-based representations I will get into and show some pros and cons that we can use for it. So now, if you look at this computation, what I showed you before, so I have the CSR. If I do a C-tree representation, that's a kind of a hybrid between pointers and arrays. You get about 30–40% slower. Even the gap is small. This is a long time, so it's actually matters slower than using CSR. And if you use binary search trees, it's probably 2x slower than doing that. Why do you want to pay this cost? Because now your insertion cost goes down drastically. So if you do the most pointer-based binary search tree, page rank is a little bit more expensive, but insertion is very, very cheap. C-tree is somewhere in the middle. Again, but still it's multiple orders of magnitude better than trying to take your CSR array and insert something in here. So let's try to figure out now I need to generate code. If you like this data structure, can we use generate code to do that? So I'm going to show you what it takes to do, start this looking at doing two matrix element-wise multiplication. So A, B times C becomes A. If it is dense, very easy. You get this very simple piece of code that everyone knows how to write. However, if B is a block cleans list, you have to generate these multiple map functions and iterate over that and generate a little bit more different code. And if it is a binary search tree, you have to generate another set of code that's more complicated but very different from the others. However, all these things have this nice property. Only one was this linked data structure. Other one is a dense array. Nice thing about dense arrays is you can keep looking up the values in here. If both are sparse pointer-based data structures, you need to end up creating code something like this. And now you will realize why we need a compiler, because if you want to do this manually for every darn thing you want to generate, it's not going to scale that well. And every time you change the format a little bit or the operation a little bit, you have to generate pages of very complicated code. And write in the manual, you probably the debugger better than what we saw in the last keynote. So this is what debuggers come in handy. So we want to generate code. So we want to make You don't need to use debuggers. So how do you deal with this very complicated data structure? So this is the different data structures. Each data structure has some use somewhere, depending on the data shape, depending on how much insertions versus computation, what type of computation, different data structures matter. And as you go multiple different, multiple dimension tensors, these data structures become very complicated. But what we figured out was the same way we did level format, we can use level format concept in here. So what you can do is the first level for these two data structures is binary search trees. And then for the first one, the next level is also binary search tree. The next level could be C tree. So this look like a complicated structure, but level by level, you only have few different data structures to deal with in here. These two representations, first level is dense, and here the second level is just a linked list. Third level is a block linked list. So you can have these combinations to basically do that. But now you realize there's so many different combinations of different type of data structures you can use. Algorithms people go happy writing very thick books about hundreds of different data structures. Now we as compiler people have to deal with that. So how do you do that? We came up with this language called a node schema language to precisely define these data structures. So here's the node schema language for a binary search tree. So first, I have element in that data structure. That element is not empty in there. And I have a left tree, which could be empty or not empty, which is also a recursive definition of a binary search tree. I have a right tree. And then other interesting thing we added is because the data can be ordered, the left tree has elements smaller than my element, and the right tree has elements that are all larger than my element. So that is the order in here. Yes, in here. So that gives you the order of data representation. And this lefty, middle, and that data goes in that order. So using these, we can actually nicely describe this tree. And in fact, we have defined a language that we can use to describe many pointer-based data structures. That's a combination of arrays, pointers, and a lot of interesting things in there. A lot of interesting data structures fits in here. So for example, in this data structure, the inner dimension is a C tree. So C tree says I have element that's non-empty. Then also I have a list of basically array of elements that are non-empty, and then I have a left and right tree that can be either empty or not empty. And this list has a size B, and my sequence is left has a smaller value, then my value, and then the next set of values are in my array, and they are also ordered. That bracket says they are ordered, and then the right tree in here. So I get that description. In here, if I have linked list, I can just say I have a non-empty element, and then there's a recursive differential on linked list, and I have a smaller value than all my people behind me. And then block linked list, I have a non-empty block in here, and then I have recursively going afterwards, and the block could be 0 to 2, and again I give the order in here. So this, and as you can think that I can represent much more complicated tree structures out of that. Now I want to generate code. So since we say that we can do by level, just look at one level. So that means you're looking at vectors. I am doing element-wise multiplication of two vectors. So assume I am getting one output and one input at dense. One is a binary search tree. So I get my data structure representation I need to compute. And if the binary search tree is present, I go to the element and say, haha, get that element, get the value, do the computation. And I can do this by looking up C value for my index I got for that element. And then if there's a left tree, I have to do it before because it has smaller values. And the right trees, I have to do after that has values afterward. I recursively compute that. So I get this value in here. That's great. And if I can add some pragmas, I can actually even get this parallel. And this is all very simple and mechanical to do, so the actual compiler can do this. However, if one thing you have noticed in here is the sparse structure, binary search tree runs the show. It's what actually do all the control. And when you have to deal with dense array, I'll just look up because I can look up any value at a given index. I can do that. However, if both are actually sparse, that's not possible. So first I will show you how to do that. So instead of trying to generate something complicated, what you can say is there's something that's each of these sparse things, I can build iterator. And recently in C, you have this yield function. So what you can say is I build that iterator, this is very similar to what we did before. And when I reach my value, I yield the value. And if there are left and right tree, I will iterate down through that and yield in the value in the right order. So I can the iterator do this welding. And so now, if we have these two different data structures, so assume these two different data structures were list in here, what you have to do is you have to do a two-finger merge through this list iterating down there. Now, if you change one of these data structures to binary search tree, I just only have to take and do a simple modification, this two-finger merge, to basically make it possible to have a binary search tree, a two-finger merge with a compressed array in here. And if both are some pointer-based data structures, we can create two iterators and do this two-finger merge here. So by doing that, we can actually iterate through that. Finally, we can do some optimization. So here, in this one, what you see is just a lot of recursion in here. So first simple thing we can do is do some tail call elimination. But also you realize I am calling recursively just to get this tree recursive through the tree, but you have to do stack pointers, registers, all has to get spilled in and out, inefficient. So the final thing we do is we implement our own stack just to do the recursion through the tree, and by doing that we can get the very good performance. I'll finish by showing some performance. So I'm comparing Taco again, multiple systems. PAM is basically doing a simple set of database operations basically in there. And they have implemented it using binary search tree. And Aspen, Stinger, and Terence is three systems that are doing graph optimization, graph operations. And each use different type of data structure. These are all handwritten data structures. And what we're showing here is our generated code outperforms everything. And we can basically do all the operations they have implemented. However, because Aspen, Sting, and Trans all basically is very specific graph, they only have few kernels implemented. PAM is a little bit more general. So from PAM, you can do other operations. But the way PAM does is it uses a bunch of small kernels and create intermediate values. So the intermediate values can really blow up in your face. So a lot of them are a lot more costlier, whereas we directly compute the entries also, we can get really good performance. So in conclusion, so efficient code for computing on dynamic sparse tensors can be automatically generated from high-level specification. We can generate many different, very interesting data structures automatically. And adding support to new structure is not that difficult. We have language, you can use that language to do that. And our techniques make it simple to exploit these different formats, and we can do combination of different formats in a complex expression. So some could be dense, some sparse, some could be array sparse, data pointer-based structures, or many different pointer-based structures in the entire single expression, and we generate all that code automatically. And we get pretty good performance. If you're interested, this work and a lot of other previous sparse compiling work is available from this site. Let me stop here and take some questions.
Hey, great talk and great work. So you sort of mentioned this kind of at the end here, but one of the reasons that we have so many different formats is that depending on what kind of computation you want to do with a particular sparse tensor, you might need different formats. Yes. Now, if you have multiple expressions in a larger program, one of the things you might need to do is switch formats and maybe choose one format that's best across all of the expressions. Do you have any sort of thoughts on what we can do in that situation?
There is this entire section, because what we have built is a mechanism. There's a policy.
Yeah.
Okay. And policy is a very interesting thing because in dense, if you're doing dense computation, the only thing affect the policy is probably the machine you run and the size of the matrix. The problem is sparse is all the things inside it. They have blocks, there are diagonals, power law, all these things. The data, in fact, itself is affecting what's happening. And then sometimes it might be good to do in between, like some kind of a transform from one format to another. Because sparse formats have a lot of restrictions how you can iterate over that. So if you want to go from a row based to a column based, you have to transform that. So there's a lot of policy decisions that have to make. And we are looking at schedules on how to do that, scheduling technology to do that. But I think there are two levels. One is just do the dumb, simple thing and then get away and don't screw up on asymptotics. Because here, a lot of small changes can have asymptotic cost in here. So if you get asymptotics right, but forget the rest in there, and that we can do. And the other thing is just do a full search and figure out the rest. Problem with that is you have to amortize the search because sometimes if you do a real one, you have to actually look at inside the tensor, look at the patterns, and if you're just using the tensor for once, that cost itself might be prohibitive. So if you're iterating over that much product, so there's a lot of interesting things in here, and I think it's very interesting.
Very nice talk, very clear talk. Thank you. I have a few questions. So since you are going over the pointers, there should be 2 times overhead compared to if you're just doing in a standard form. Is that correct?
Not really, because something like a C tree, there are pointers, but also there are arrays inside this thing. So what you're doing is you're using pointers judiciously. And then, so if you want to insert something, yes, you might have to change array of 256, not array of 2 million. So you mix and match those things. If you do it right, you can get the right balance between low insertion cost and a very fast iteration cost.
So have you done any experiment like taking the CST format and doing some computation and your approach, and what is the kind of compared to slow down or performance?
So if you look at, I think this is probably the closest I will have for right now. I mean, we can take this offline, but let me show. So something like this will show that, in fact, the difference between doing some computation from the left-hand side, these are all logs of big numbers, even though small, versus insertion time. So this is, again, you're not looking at the data shapes, and the data shapes might have. So that space is very interesting, extremely. I don't think people have done too much interesting work there. That's opportunity.
Thank you for the talk. I have 2 questions, and the first one is because I'm not familiar with the Nova schema language. Is this one particular for expressing the interactions of like the different layers that you have like in the data structure, or can you also like express like more implementation details like bit compression or constraints between different nodes?
Yes. This is only for one level. And then when you each level at the bottom of the thing has a data, and if it's a multidimensional representation, the data will be yet another representation. So there'll be another thing embedded there. It becomes sometimes complicated things like when you have array, that means the data process, like for example, a single array. So there are certain complexities we don't handle at this point, but you can do that. We have tried to do many different interesting representations, but we can chat to see whether representation of your choice that we can do.
Yeah. And the second one is like you described why you need compiler basically because you have many different building blocks for expressing sparse tensors. So my question is also like going the other extreme. Based on personal experience, there's a lot of power, for example, having like a single sparse abstraction, for example, like a tree-based abstraction that, especially for example, if those abstractions can be, for example, canonical in the representation, you can do a lot of like operations like on the structure inside efficiently. So did you explore that spectrum as well?
So I think that's a very interesting question. This is a slide I didn't actually put in here. In dense, you can create one set of a representation and have binary operations. And you can say, I have, you can build any complicated sort of binary operation. The thing about sparse is You can't do that. Because if you do binary operations, you might create intermediate that asymptotically rather than what's needed. Because the thing about sparse is if you multiply by 0, you don't have to do any computation on the side. So if you do a times b times c or something like that, if I know everything, if I say this get multiplied, Google is sorting out silly. If I know that at the end of the day, that thing will get multiplied by 0, I can not calculate it. So because of that, the premise of creating a simple library of binary operations doesn't work. So that means any compound operation has to be generated to basically get that advantage. So that itself needs a compiler because that means every compound operation has to be generated. Now that on top of that, if you have operations that take 3 different arguments, each can keep different representations. It makes sense because if you are doing a lot of insertions or into something versus very little, different representations make different cost benefit analysis. So finding one way you will get something, but it's not the best thing. The best thing is figuring out your representation, figuring out the pattern in here, and then do. For example, if you have blocks of data, some kind of block representation can be sometimes ordered by the direction. So this one representation idea falls down as you look at this kind of nuances here. So if you really want to get performance, you need to have multiple representations.
Thank you.
Sorry, that takes us offline. Thank you very much, Tom.
Thank you.